This video is about a very simple problem. Any teenager can understand it, but only one teenager was able to solve it, 2,000 years after it was posed. We're talking about polygons. With only a compass and a straight edge, which ones can we construct, and how, and why did it take so damn long to figure out? We'll begin in ancient Greece, exploring the origin of construction problems, the progress those mathematicians made, and why they got stuck. Then we'll journey through to the post-Enlightenment era of complex numbers and polynomials, exploring what these ideas have to do with compass and straight edge constructions, and how they were used to solve the problem. And by whom? Because while one of the solvers is well known, the other was never appreciated in his time and deserves greater recognition. I hope you enjoy. From the Greek poly meaning many and gon meaning leave, a polygon describes the common audience reaction to a mathematician telling jokes. But a simple polygon is a bunch of line segments joined end to end until they form a complete chain. A polygon is regular when all these line segments are the same length and all interior angles are equal. The problem is, which ones can we draw? But not so fast, there are some rules. Protractors and rulers, get out of here, because we are only allowed to use these. A straight edge, this is like a ruler, but without any markings, so we can use it to draw line segments, but not to make measurements. And we can use a compass. We can use it to draw circles, arcs of circles, and we can use it to duplicate lengths. So for example, let's construct the simplest simple regular polygon, an equilateral triangle. Start with any old line segment, stab one end and draw an arc from the other end, repeat here and connect these up. Note that these are the same length because they're both radii of this circle here. Similarly, these two are both radii of this circle, so they are the same. Thus, all three lengths are the same, and this is an equilateral triangle. Usually, we'd need to check the angles, but this is sufficient for a triangle. So under these restrictions, which regular polygons can we construct? Also, why compass and straight edge? Well, it stems from ancient Greece and mathematicians like Euclid. This triangle construction is actually the first proposition proved in Euclid's Elements. The earliest known treatise on mathematics with an axiomatic approach. That approach is, given a handful of assumptions, what can we prove as a logical consequence? Fans of my channel will know that I love building theory from the ground up, and this is what I adore about Euclid. Nowhere in here does he discuss usefulness or applications, it's just an act of pure creation. Anyway, Euclid makes 5 assumptions called postulates, and of interest to us are the first 3. Between 2 points we can draw a line segment. A line segment can be extended. Given a point and a distance, we can describe a circle with that center and radius. These postulates essentially say we can use a straight edge and we can use a compass, tools which were easy to make at the time. This is the origin of compass and straight edge constructions, and they were very important to Euclid. Book 1 of the Elements begins with the construction of the equilateral triangle, and the final book ends with the construction of the 5 Platonic solids. The solids are a story for another time, but let's turn our attention back to regular polygons and keep track of which ones we are able to construct, as Euclid actually knocks out infinitely many of these. The square comes in Book 1, Proposition 46. This is after Euclid shows us how to build perpendicular lines at an arbitrary point, how to duplicate angles to an arbitrary position. He proves that alternating angles are equal on parallel lines, how to construct parallel lines through an arbitrary point, and he proves that if ABCD is a parallelogram with 2 adjacent equal sides, then it's a rhombus. I've kind of glossed over these because this isn't a video about all of Euclid's elements, it's a video about regular polygons, so I'm going to assume these results for the rest of this section. If you're more interested in the derivation, see the links below. So for the square, start with some line segment AB, make a perpendicular at A, plot C such that AC equals AB, make a line parallel to AB at C, and a line parallel to AC at B. By alternate angles, this is a right angle, and by the definition of a right angle, we can say this is a right angle, which by alternate angles shows this is a right angle. Similar reasoning up here, and by construction, AB equals AC, and this is clearly a parallelogram, so by this result, we have that this is a rhombus, but because all of the interior angles are the same, it must in fact be a square. There are easier ways, but this is how Euclid does it. Euclid constructs the regular pentagon much later, in Book 4, Proposition 11. This construction is quite ingenious. A few propositions earlier, Euclid proves that we can construct an isosceles triangle whose base angles are each twice its third angle. That implies that each of these two base angles is 72 degrees. Now, Euclid uses this in quite a cumbersome way to construct a regular pentagon. I'll depart from Euclid now to show you a construction that'll help us to understand the rest of the video. So we draw a circle with one of these 72-degree angles in the center. The thing to note is that 72 degrees is a fifth of 360, it's a fifth of a full turn. So duplicating this whole thing 5 times will give us a pentagon. Now we should just convince ourselves that this is regular. So all the side lengths are the same length by design. As for the angles, draw in these remaining radii. By side, all 5 of these triangles are congruent, hence all of their angles are the same. But every interior angle of the pentagon is the sum of 2 of these angles, so all interior angles of the pentagon are the same. Embedding polygons in a circle is going to be so essential for the rest of the video that I want you to burn this image into your mind. Realize that what we did for the pentagon, which was to plot 5 points on a circle equally spaced, can be generalized. So long as we can plot n points equally spaced around a circle, we can connect them to form a regular n-gon. Euclid shows us how to use this idea to construct a regular decagon, which has 10 sides. Simply draw perpendicular bisectors of each edge of the pentagon. These bisectors also bisect the arcs of the circle. So these 10 points are now equally spaced around a circle, and joining them will create a regular decagon. We can repeat this doubling trick for a 20gon, 40gon, but also start with a triangle or a square to make a hexagon and so on, and an octagon and so on. Thus, Euclid shows that we can construct polygons with side number equal to 2 to the nth times 3, 4, or 5. But Euclid actually goes further. In Book 4, Proposition 16, he constructs a pentadecagon, or a 15gon. To do this, start with a circle and inscribe a regular triangle and pentagon sharing a vertex. The goal now is to construct 1/15th of the circumference. That way we can generate 15 equally spaced points, and I invite you to pause now and consider how we might do it. Well, since the triangle gives us a third of the circumference, and the pentagon gives us a fifth, if we do 1/3 subtract 1/5, then we'll get this arc here, and that comes out to be 2/15ths. Therefore, if we bisect it, that will give us 1/15th of the circumference. Repeating that will generate the 15 vertices of a regular 15gon. We could then apply the doubling trick to a 15gon to generate a regular polygon with side number 2 to the nth times 15. So are there any more? What about constructing regular heptagons and nonagons and so ons? All we need to do is construct, say, a 7th of the circumference for a heptagon. Well, Euclid never managed to do it, and nor did any of the ancient Greek mathematicians. They also didn't prove it was impossible. Such was the case for many problems of that era, most famously this trio: squaring the circle, trisecting the angle, and doubling the cube. What is it about these problems, as well as constructing regular polygons, that gave the ancient Greeks such a hard time? Well, I think they were limited by their concept of numbers. I explored this more in my video on whether 1 is prime, but Euclid defines a number as a multitude of units. All other lengths are just general magnitudes and not numbers. And confusingly, these magnitudes are not rational or irrational in their own right, they are rational or irrational with respect to other magnitudes. This is confusing by modern standards. For example, I won't go into the full details, but his definition implies that if 1 is rational, then the square root of 2 is rational, because 1's square can measure root 2's squared, whereas the 4th root of 2 would be considered irrational. On the other hand, if the 4th root of 2 is rational, then any integer is considered irrational. It feels like Euclid's concept of numbers was centered around what could be constructed. That which can be constructed are things that exist, and if it can't be constructed, its very existence is unclear. This might be why Euclid never discusses negative numbers or cube roots. He couldn't construct them. This was a problem, as doubling the cube is the problem of, given a unit cube, construct a cube of double the volume. Its side length will therefore be the cube root of 2. So this problem is essentially to construct a cube root. Cube roots are also required for trisecting an arbitrary angle, though the reasons are less obvious. And if we could trisect an arbitrary angle, that would open the door for more polygons. For example, if we could trisect an angle, we could start with the triangle, trisect that angle in the middle, and that would generate the points of a nonagon. Nowadays, we're happy to consider the cube root of 2 as just an abstract entity, that which, when cubed, gives 2, and who cares if we can construct it? It could be this missing level of abstraction that prevented the ancient Greeks from finding solutions to these problems. But to be fair to the ancient Greeks, they made the only progress that was ever made on this problem for over 2,000 years. Elements was written around 300 BCE and no one added to this list until 1796. That's crazy. What was missing? Well, quite a lot. So this is where we leave Euclid and embark on a journey of knowledge. Kind of a hero's journey, leaving the safety of compass and straightedge, venturing through the innovations developed through history, and then returning to constructions with an enlightened understanding. And hopefully our mentor won't die along the way. Come with me. Our first goal is taking things out of the world of plane geometry and into the world of numbers. That's because in the plane you have so many options for moves you can make, it's very difficult to see what is and isn't possible. But it's comparatively easier to analyze numbers to see which are constructible. So for now, forget about shapes and angles and just think, if this length here is 1, what other numbers can we make? Well, we can duplicate it to make any positive integer. Moreover, using Euclid's propositions, we can start with any lengths a and b and construct a divided by b. Draw them at some angle like this, mark off a unit length on b, complete the triangle, and draw a line through the end of that unit length that's parallel to the line that completed the triangle. This forms a length on a I'll call x. Now notice that these triangles are similar, so the ratio of the lengths x over 1 is equal to the ratio of the lengths a over b, and thus this length x equals a over b. A similar construction, pun always intended, allows us to construct a multiplied by b. And I think it's pretty clear how we can add and subtract lengths, either by extended a by a length of b, or trimming a by a length of b. So the numbers we can construct are those which, using integers, repeatedly add, subtract, multiply, and divide. What we would call today rational numbers. But we can actually do a bit more than that. Starting with a length a, we can construct its square root. To do this, join a unit length on one end, bisect the whole length, and then make a semicircle with the whole length as its diameter. Make a perpendicular here, forming a length x, and then join these lengths. By Thales' theorem, this here is a right angle, and we can see that these two triangles are similar. And we know the drill by now, the ratio x over 1 will be the same as the ratio a over x. Thus x squared equals a, and therefore x is the square root of a. So the numbers we can construct are those which involve integers, repeated use of the 4 basic operations, and square roots. We see this influence today on basic calculators. The numbers we can construct in the plane are the same as those we can make on a basic calculator. Your inputs are the integers, the 4 operations, square roots, and nothing more. I want to solidify this step with an example. Let's construct the following horrendous number. This looks like a nightmare, but we can break it down step by step. Starting with the unit length, we can create 5, then its square root, we can build 7 and build 6, therefore build 7 over 6, then we can stick them next to each other to add them, and then construct the square root of that. Then we can build 3, we can build root 3. It's at this point I realised that this will actually come out to be a negative number. Don't know how I missed this when I was writing my script, but there we go. Now we can do that. We can kind of double back on ourselves and create a negative, but at this point in history, negative numbers weren't really accepted, so in keeping with that, let's just tweak this to make it a positive number. I'm going to make this 5 lots of this value here. So we'll take 5 lots of this first term and subtract 4 lots of the second. At this point, I was really curious how accurate our construction is here, because these constructions are basically impossible to do accurately in practice because of all the little inconsistencies that build up. But let's just check it anyway for fun. This comes out to be approximately 2.3, and now our unit length in millimeters is about 26. 2.3 lots of this unit length of 26 millimeters comes out to be about 59.8. And now if we check, looks like we have about 63, so not a million miles away, but you can see how it's actually really difficult to do these in practice. These types of numbers are called constructible numbers, and what does it mean for polygons? Well, if the side length of our regular polygon is constructible, then we can construct it using compass and straightedge, and then using this circle trick, we can duplicate that length around the circle and thereby constructing it. So really the question becomes, when is the side length of a regular polygon a constructible number? So that's our first step, and you might be wondering, sure, we can make those kinds of numbers, but we haven't proven that we can't make anything else. It's a good point. How do we know that we can't make, for example, cube roots? It's just that no one has figured out how yet. Well, this is the first of many hanging questions we'll discuss later. The answer lies in equations, because as we know, when we're trying to determine numbers given constraints, a natural way to do that is to establish and solve an equation. So that is our next stop. The Middle Ages saw a surge in understanding of equations and a profound rethinking of our understanding of numbers. Diophantus of Alexandria was the first known mathematician to accept rational numbers as, well, numbers, and write the first recognizable algebraic expressions, though his notation is difficult. But Middle Age Islamic mathematicians built on this, with those like Al-Kamil treating irrational quantities as numbers in their own right. Al-Mahani's concept of rational as a number which can be expressed quantitatively, and an irrational as one which is impossible to pronounce and express quantitatively, is close to the modern definition, as irrationals are necessarily those which have a non-repeating, non-terminating decimal expansion. We can't write them down, we just have to use some notation. Later, Al-Khwarizmi developed a systematic way of dealing with quadratic equations. It's clear that these mathematicians were much more comfortable with irrational numbers as abstract entities which could be tangibly defined, even if we couldn't construct them geometrically or write them down. Many of these notions were also developed in India, where mathematicians like Sridhara developed a means of solving quadratics akin to the modern quadratic formula. I'm told that this formula is still taught in India as Sridhara's formula, and it's in this formula we see a link to constructible numbers. Note that this formula uses only the 4 basic operations and square roots. This hints at the next bridge, which is that a number is constructible if and only if it can be reached through a chain of quadratic equations. Now, admittedly that was a mouthful, so let me break it down. Imagine I have a constructible number formed from applying the square root function exactly once. We can do the other 4 operations as many times as we like. Well, then start by building the thing you intend to root. Notice that by adding, subtracting, multiplying and dividing, you just end up with some rational number. Call it t, and then we root it. Now notice that no matter how much you add, subtract, multiply and divide from that, you just end up with some rational number out here, call it r, and some rational coefficient, call it s. So all constructible numbers with one root look like r plus s root t. And now I claim that this is the solution to a quadratic equation with rational coefficients, namely this one. I'll leave it as a pretty simple exercise to verify that, and conversely, say that I start with any old quadratic with rational coefficients, say ax squared plus bx plus c. Well, then we know its solution, which is essentially in the form r plus s root t. So there we see it, a number is constructible with one root, if and only if it is the solution to a quadratic with rational coefficients. Okay, but what if I apply the square root function multiple times? Well, then we can build up to this number with a chain of quadratics. Starting with just the rationals, we can solve a quadratic to obtain a number that involves roots. So then we know this is constructible and we can use it in future quadratics to obtain more constructible numbers. And we can repeat as many times as we use the square root operator. The notation is getting messy, don't worry, we'll clear this all up with an example shortly, but again, I think of it like the basic calculator. Each time we solve a quadratic, we add its solution to a new button that we can use in future constructions. So for example, remember this horrible number? We've already constructed it using compass and straightedge. Let's construct it again, but let's do it the quadratic way. And like when we did it with compass and straightedge, we just do it step by step. So square root 5 is the solution to this quadratic. As the solution to a quadratic with rational coefficients, it's a constructible number and we can use it in the future. Similarly, root 3 is a solution to this quadratic. And again, as a solution to a quadratic with rational coefficients, it's a constructible number and we can use that in the future. And now I claim that our number is the solution to the following quadratic. Again, I'll leave it as an exercise to verify, but the intuition here is that every application of the square root function introduces a new layer of quadratic. So this number having two nested roots will be a solution to a quadratic that has roots in its coefficients, and a number with a triple root will require double roots in its coefficients, and so on. So why do this? Well, now there's a tangible connection between that which can be constructed with compass and straightedge and that which can be obtained via a chain of quadratic equations. And remember, equations are good because with them we can analyze what is and isn't possible. Linking this back to regular polygons, so long as the edge length can be formed from a chain of quadratic equations, we can construct it. So now, how do we get our hands on these edge lengths to see if quadratics can be used to build them? Well, that's where we need the next stepping stone. And this is quite a long video. Thank you so much for sticking with me. I hope you're enjoying it, but if you do need a quick break, now would be a good time. Do not worry if you've never seen imaginary numbers, I will tell you everything you need to know. And indulge me in a quick history lesson, because I think it's a cautionary tale that goes some way to explain why this problem remained unsolved for so long. Echoing the Islamic mathematicians who grew more comfortable with increasing levels of abstraction and considering irrational quantities as numbers, post-Enlightenment mathematicians took things further. Just as earlier we said that the cube root of 2 is just some number which when cubed grants 2, now imagine that the square root of -1 is just some number which when squared gives -1. Like we said earlier, we can't write down the cube root of 2, so we just use some notation like this. Similarly, we can't write this number down, so we just use some notation, typically I. These numbers, like irrationals before them, weren't accepted for a few centuries. But this is the cautionary tale I alluded to earlier. In rejecting types of numbers, certain problems were out of reach for earlier generations of mathematicians. It's the same story here, and you might have noticed another type of number conspicuously missing: negatives. You might be surprised to learn that negatives were only accepted in the West about as recently as these, which are called imaginary numbers. It's an unfortunate name coined by our old friend Descartes. If you've seen my video on his rivalry with Fermat, you know he's quite the character. In his seminal work, La Geometry, he discusses polynomials, noting that a polynomial has as many roots as its degree. Quadratics have 2 roots, cubics have 3, quartics have 4, and so on. But he says that some of these are false roots, like this quartic here, which has a false root of x of the form x plus 5 equals 0, i.e. a negative. He calls them false roots because Descartes didn't consider them a genuine solution. Similarly, when discussing cubics, he says that while some roots are real, others are imaginary, and this is the first recorded use of the term. Imaginary stuck, and even later, Leonhard Euler introduced the notation I, and it was in his time that the numbers gained acceptance and a relevance to us, meant that solving this polygon problem was finally in reach. So, history lesson over, what do imaginary numbers have to do with polygons? Well, it turns out imaginary numbers are just great. Eugene Wigner once described mathematics as unreasonably effective in the sciences. There's an argument to be made that complex numbers are unreasonably effective in mathematics. Firstly, let's complete our number system now that we're happy to accept all kinds. We can take multiples of I, and they can be thought of as square roots of other negatives. Root negative 9, for example, is 3i. Also, it's minus 3i, so we can have negative amounts of I as well. Most of us visualize a number line with all of the numbers we know and love. Positive, negative, zero, rational and irrational. These are what we call the real numbers. Perpendicular to this, we have the imaginary axis. Positive amounts of I, negative amounts of I, rational and irrational amounts of I, and so on. Numbers now no longer fit on a line, but in a plane. This number here has a bit of real and a bit of imaginary. We call it 2 plus 3i. This one here is minus 1 plus 2i. This is 4 subtract i, and so on. These are called complex numbers. Not complex as in complicated, but complex as in consisting of many parts. A real part and an imaginary part. Of relevance to us is an amazing property they happen to have, and this is where we will find our polygons. So what happens when we multiply some of these together? Let's do it. Let's do 2 plus 3i multiplied by minus 1 plus 2i. Crunching through the algebra, remembering that I squared is negative 1, we get negative 8 plus I. Just kind of randomly out here. Is there any intuition for why this is the answer? Yes. It turns out that if you measure the distance of each to the origin and multiply them, we get the distance to the result. Using Pythagoras, you can verify this result. More than that though, if we measure the angle from the positive real axis, it turns out that the sum of the angles is equal to the sum of the result. If you like, you can use some basic trig to verify this result as well. Now this is an extremely powerful property. I'll leave it as an exercise to prove, I'll leave some hints here on screen if you need them, but now look what happens if I only consider numbers which are a distance of 1 away from the origin. So if I take these two numbers which are a distance of 1 away from the origin, the distance to the result will be 1 times 1 equals 1. In other words, if we take a circle of radius 1, multiplying two numbers on the circle will give us another number on the circle, and to find it, we just add the angles. So, and I'm so excited, if we take the complex number at 45 degrees and multiply it with the one at 90 degrees, the result will be the one at 135 degrees. And doesn't this look familiar? In fact, if we take the one at 45 degrees and square it, we get the one at 90. If we cube it, that's 3 lots of 45, so 135. If we take it to the power of 4, that's 4 lots of 45, so that we get the one at 180, and so on. And you see now what we've done. We've generated 8 equidistant points, in other words, a regular octagon. So here we find a very natural way to embed regular polygons in the complex plane. How awesome is that? Now this works because 45 is an eighth of 360. If I choose another angle, like 360 divided by 6, which is 60, we'll obtain a regular hexagon. In general, to construct a regular n-gon, we need to start with an angle of 360 over n. So the question is, what exactly are these numbers? Because we want to know if they are constructible. For example, back to the octagon, what is this number z, a distance of 1 from the origin and at an angle of 45 degrees? Well, to find its real part, we can resolve down. Using some basic trigonometry, we see that this length here is cos 45. And as for its imaginary part, we'll get sine 45. So this number is cos 45 plus I sine 45, which we know to be root 2 over 2 plus root 2 over 2i. This is a constructible number because we can make them using the 4 basic operations and square roots. And that's why the octagon is constructible, which we've known since the time of Euclid. But what about polygons we haven't constructed yet? Say like the heptagon. Well, this first complex number here is at an angle of 360 over 7. So it is the complex number cos 360 on 7 plus I sine 360 on 7. And the question is, are these numbers constructible using only the 4 operations and roots? Well, this is where we bring the idea of quadratics back into play, because actually, we know they are constructible if there is a chain of quadratics that we can solve to get the answer. And this is the great innovation of none other than Gauss. Before we get into that, just a bit of housekeeping. These complex numbers here have the fancy name of roots of unity. Root like nth root and unity meaning 1. Here, for example, is the 7th root of 1, because if I take it to the power of 7, I get 1. Notice also that z to the power of 8, well, that's the same as z to the power of 7 times z. Z to the 7th is 1, so this is the same as z. Similarly, z to the 9th is z squared, z to the 10th is z cubed, and so on. We can take the powers modulo 7. That'll be useful later. Now, we've already said that these generate a regular n-gon. The last fact that we need is what happens when we add them all together, including 1. So there are a couple of ways to see this. I'll give you the intuitive way and the algebraic way, because both of them are pretty quick. The intuitive way is that these are all symmetrically spaced around the circle. So by adding them, we're going to get 0, because 0 is like the center of mass of all of these roots of unity. The sum can't be biased one way or the other by symmetry. I'll also give you an algebraic reason if you're not satisfied with that. So for this, instead of the 7th roots of unity, where I add 1 plus z squared right the way around to z to the 6th, I'm going to do it for a general nth root of unity, where I do 1 plus z squared all the way around to z to the power of n minus 1. Now watch what happens when I multiply this whole sum by z minus 1. Well, multiplying them all by z just increases all the powers by 1, and then we just subtract the original sum. I am so sorry that I never ever leave enough room for that bracket over there. Anyway, we can see that most of these terms are going to cancel, so the z will cancel with this z, and so on, and everything will die apart from the z to the n here and a minus 1 there. But because z to the nth is equal to 1, this is equal to 1 subtract 1, which is 0. So this times this equals 0, and this isn't 0 because z isn't equal to 1, it's some complex number up there. So this is 0 as required. So that's that, and now we are ready for the final stage where it all comes together, where Gauss was finally able to add to this list over 2,000 years later. Just as a reminder, the goal is to build this root of unity with a chain of quadratic equations. That will show that it is made from constructible numbers, meaning we can build it with compass and straightedge, taking us right back where we started. Gauss noticed a way of splitting the roots of unity into convenient groupings which have delectable properties. As you're about to see, it's those nice properties which allow us to build the chain of quadratics. Sadly, Gauss's method only works for nth roots of unity where n is prime. Why? Well, that's another hanging question we'll address later. So, Gauss deployed his method on one of the unconstructed polygons with a prime number of sides. But not a heptagon, not an undecagon, not a tridecagon, but a heptadecagon with 17 sides. Why 17? Again, we'll come back to it. So here's what Gauss noticed about splitting up the roots of unity. Start with z, and then repeatedly square it. Generate z, z squared, z to the 4th, z to the 8th, z to the 16th, then z to the power of 32, which remember is the same as z to the power of 15, and then z to the power of 30, which is the same as z to the 13th, then z to the power of 26, which is the same as z to the 9th, and then if we square that, we'll get z to the power of 18, but that's the same as z. So from here, this will just repeat itself. So this squaring operation repeats itself every 8 steps. It is what we call periodic. What if we start with a different root? Well, notice if we start from any of these and start squaring, we'll just generate the same 8 roots. So what if we start with a root we don't have yet, say z cubed? Well, that generates these, and if I square z to the 10th, I get z to the power 20, which is the same as z cubed, so this also repeats itself every 8 steps, and this perfectly partitions the non-trivial roots of unity. That's all the roots of unity except for 1. These are the splittings that Gauss discovered, and the sums of roots of a given splitting have interesting properties. And it's these sums which are known today as Gaussian periods. So squaring produces 2 periods of length 8, but what if we choose a different power? Well, notice if we do to the power of 4, that's like squaring and then squaring again. So this will just give us every second term in the length 8 periods. So this splits the roots into 4 periods of length 4. Likewise, raising to the power of 16 is the same as raising to the power of 4 twice. So these will take every second term in the length 4 periods, and this will partition the roots into 8 periods of length 2. Now, what are these nice properties that I keep talking about? Well, I'll tell you. But exactly why these properties are so nice will only become clear shortly. First, notice how they can be chosen such that summing two of them will add up to a larger period. So for example, if I add these two together, I get this length 4 period here. Also, think about adding these two length 8 periods. That's the same as adding up all of the roots of unity except 1. And we know that adding up all the roots of unity, including 1, equals 0. So adding up these two will sum to -1. They can also be chosen to have nice products. For example, look what happens when I multiply these two. There's 16 different products going on here, so I'm going to do it like a grid. And notice we've got exactly one of every non-trivial root in here, so this product is just -1, as we just justified up here. So it's nice and everything, but who cares? Well, the fact that they have nice sums and products is exactly why we are able to form a chain of quadratics. So, I hope you're ready, because here is how Gauss proved that the heptadecagon is constructible. First, we actually need all of this information, so let me just grab it on this board Minority Report style. I'm going to name the length 8 periods alpha 1 and alpha 2. The length 4s will be beta 1 through beta 4. And the length 8 will be gamma 1, gamma 2, and if you're wondering about the other 6 length 2s, we actually don't need them. So we'll keep all this information on here and add to it as we go, and now the goal is not actually to construct Z, it's to construct gamma 1. Let's just briefly talk about why that is. Well, remember that Z is cos of this angle plus I sine of this angle. But by symmetry, Z to the power of 16 is the same, but with the imaginary part negative. And therefore, if we add them, we just get 2 cos 360 on 17. Therefore, cos 360 on 17 is half of gamma 1. And what's the significance of that? Well, cos 360 over 17 is this length here. And if this length here is a constructible number, then I can draw it. I can draw a perpendicular line upwards to the circle, and that gives me my first point, and then I can duplicate that around the circle. So if we can make this, we can make the regular heptagon. And we can make this if we can make gamma 1. And gamma 1 is constructible if it's the root of a quadratic. So let's build a quadratic such that gamma 1 is a root. I'll also let gamma 2 be the other root. But that's if and only if these are its factors. So the quadratic is just the product of these two factors. Expanding, we obtain this, and this is where the niceness of these Gaussian periods comes into effect. So this gamma 1 plus gamma 2 is actually beta 1, and this product gamma 1 gamma 2 is beta 2. Now this is a quadratic, and we know how to solve quadratics, so let's stick this into the quadratic formula. Now remember, gamma 1 and gamma 2 will equal this, so let's just work out which one is which. Gamma 1, being z plus z to the 16th, is going to be quite a large positive number, while gamma 2, being z to the 4th plus z to the 13th, is going to be a smaller positive number. So that means gamma 1 will correspond to the plus case, and gamma 2 to the minus case. So I'll keep that information on here, and I actually don't care about gamma 2. Now, I know now what gamma 1 is. It's this, but if only I knew what beta 1 and beta 2 are. So, that's our new goal. Well, that means I want quadratics where beta 1 and beta 2 are solutions. I'm actually going to pair beta 1 with beta 3 and say let's have a quadratic where beta 1 and beta 3 are the roots, and we'll pair beta 2 with beta 4 and build a quadratic where those are the roots. So again, by the factor theorem, we can derive the corresponding quadratics, and if you're wondering why I've paired them this way, you'll see why in just a moment. So once again, we expand them, and now look, beta 1 plus beta 3 is actually alpha 1, and similarly, beta 2 plus beta 4 is alpha 2. And I just realized I forgot to write the x's in here. Classic. And now I've just done it again. What is wrong with me? Anyway, beta 1 times beta 3, as we showed before, is actually -1, and that's the same for beta 2 times beta 4, and I'll leave it as an exercise to prove. These are quadratics, we can solve them, so let's apply the formula, and here's what we get. Now, is beta 1 the plus case or the minus case? And is beta 2 the plus case or the minus case? Well, let's do the same we did for the gamma 1 and gamma 2. Comparing beta 1 and beta 3, we see that beta 1 is positive and beta 3 is negative, while comparing beta 2 and beta 4, we see that beta 2 is positive and beta 4 is negative. So that means beta 1 will be the plus case of this, and beta 2 will be the plus case of that. So let's get that information down. So to recap, in order to construct gamma 1, we need to know what beta 1 and beta 2 are, And we know what beta 1 and beta 2 are, if only we know what alpha 1 and alpha 2 are. So the next goal is to construct alpha 1 and alpha 2. Now, alpha 1 and alpha 2 have nice products in and of themselves, so we'll form a quadratic where alpha 1 and alpha 2 are the roots. And you know the drill by now, we expand. Now remember, these sum to -1, and as for their product, it actually comes out to be -4. It's a big calculation, but if you do it, you see that you get 4 copies of alpha 1 plus alpha 2, in other words, -4. And now this beauty. This is a quadratic with known coefficients, so we can just solve it. We get that x is -1 plus or minus root 17, all divided by 2. As for which is which, let's consult the diagram, and we can convince ourselves that alpha 1 will clearly be positive, alpha 2 will be negative, so alpha 1 will correspond to the plus case, and alpha 2 the minus case. We're getting somewhere, because now we know what alpha 1 and alpha 2 are, so we can substitute them into here to work out beta 1 and beta 2. It's not pretty, but we can do it. Now it's just a lot of tidying up, so a half squared is a quarter, -1 plus root 17 squared actually comes out to be 1 plus 17 subtract 2 root 17, and that add 4 on the end I'm going to call add 16 over 4. And I've done it like that so I can pull a quarter out of this whole expression under the root, and then I can split that into root a quarter times the root of all this. But now root a quarter is just a half, times a half is a quarter. And 8 plus 16 is 34, so I can tidy that up as well. Then I can pull a quarter out of the whole thing, and we're done. So like I said, it's not pretty, but now we have a concrete expression for beta 1. And it's very similar for beta 3, so I'll leave you to compute that case if you want to. So now I know what beta 1 actually is, I'm going to replace it on this board here. So now we're almost there, because we want gamma 1. And we know gamma 1 in terms of beta 1 and beta 2, and now we know what they are. So now we just have to substitute them into here and work it out. And this is really, really not pretty, but we can do it. And I'll do you a huge favour and spare all of the details here, because it is just a mess, but this is what we get. I told you it wasn't pretty, but there it is. That is the value of gamma 1, which we said is 2 lots of cos 360 on 17. So if we half it, we have cos 360 on 17, which is what we need. Because all of this, as horrible as it looks, can be built using only the 4 operations and square roots. It is constructible, and therefore, if you were a more patient man than I am, you could build this with a compass and straight edge. Gauss, like any good pure mathematician, only proved that it was possible, but didn't actually provide a construction. Since then, many other mathematicians have concocted some rather elegant constructions, but the point is that we can do it. We can add 17 to the list. It is some progress on this problem. It only took 2,000 years. And Gauss. Anything is possible with Gauss. Whenever you feel terrible about what you've achieved in your life, just remember, Gauss did all of this when he was 19. Gauss made thousands of contributions, but he was said to have been especially proud of this result, even requesting that a heptadecagon be carved into his tombstone. Sadly, the stonemason declined, as such an intricate design would just look like a circle. Pfft, if only we'd spent 2,000 years not on compass and straight edge, but on hammer and chisel constructions. Obviously, Gauss was exceptionally talented, but for me, it was the acceptance of complex numbers and the willingness to play with greater levels of abstraction that granted the tools to solve the problem. Complex numbers suffer a bit of a weird reputation even today, and I agree with Gauss that part of the reason is due to the moniker imaginary. If +1, -1, and the square root of -1 had been called direct, inverse, and lateral units instead of positive, negative, and imaginary, such obscurity would have been out of the question. Fortunately, we live in a time when, so long as the definitions and derivations are logically rigorous, anything goes. Or at least, so we think. I often wonder whether we are implicitly rejecting ideas that would provide great insight on many problems which remain unsolved today. And speaking of unsolved problems, do we now know the complete list of constructible polygons? Surprisingly, no, but we do have a pretty good idea, and that's due in part to another mathematician, Pierre Wantzel. See, Gauss's method only works on prime-sided polygons, and where that prime is one more than a power of 2. That's why he chose 17 and not 7, 11, or 13. The next one is 257, which is one more than 256, 2 to the power 7, so Gauss's method can be used to construct a 257 gon. So if you're still wondering why 17, That's why. Although it does prompt us to think, why must it be a prime 1 more than a power of 2? But Gauss stated that these are the only prime-sided constructible polygons. Then we can multiply 2 of them together, like Euclid does when he built the 15 gon. And then we know that for any polygon we've built, we can double the number of sides indefinitely. So if this is the number of sides, then it's constructible. And then Gauss stated that these are the only ones, but he never actually proved it. Like, what if using a different method, we could construct others? Well, enter Pierre Wansel, who did manage to classify exactly which polygons are constructible. More than that, he also solved these ancient questions of doubling the cube and trisecting the angle, problems that have been open for thousands of years. He was never acknowledged in his time, and he died at the age of 33. This theorem at least became known as the Gauss-Wansel theorem in his honor. So let's correct history and give him the recognition he deserves. Why are these the only constructible polygons? Why don't we yet have a complete list? Why can't we construct cube roots with compass and straight edge? What about the other questions I've left hanging? Well, between Gauss and Wansel, they have the answers. I released this video on the 30th of April, Gauss's birthday. Happy birthday, Gauss. And plan to follow it up with a second part exploring Wansel's contributions on his birthday. Make sure you subscribe so you don't miss it. Thank you so much for watching. This is one of my favorite results of all time. I love the journey from something as random as compass and straight edge constructions to something as robust as roots of unity and the solutions to quadratics. I've been wanting to make it for a long time, so I hope you enjoyed the journey. A special thank you to my patrons whose names are scrolling by right now. Thank you so much. I would not be able to make videos without your support. If you'd like to support me, please see the link in the description. This has been another proof under another roof. You may now perform a polygon.